what we do need to cover. So she talked about transverse waves and longitudinal waves. Okay, this is a transverse wave. For instance, like if you drop a pebble, it's kind of like your trampoline. Okay, it'll create a downward motion of the water, and then it will rebound, go up, and then it will go out from there. So it's kind of fun. It's a wave. So some energies need what we call a medium to propagate through, and some energies don't. I think she mentioned maybe sound needs a medium. It's kind of, all a medium is stuff that it can travel through. So for instance, sound in this room is traveling through the air. Sound, if you're underwater, is traveling through the water. Okay, that both works. If you're in outer space, not so many molecules or even atoms to propagate sound. So there's that old myth, to a certain extent it's true. If you were to scream in outer space, are they going to hear you? So gravity, back to that movie Gravity. Okay, so anyway, water in this case is the medium. And like she said, they have the bumps and the, whatever she called, okay, the bumps, the top things are the crests, the bottom things are the troughs. An important thing that she talked about was the distance between crests. Honestly, you could go the distance between troughs, and it's the same thing. But that's what's called the wavelength. Up there, I'm going to go ahead and you're going to see this later, but we need to use the Greek letter lambda for wavelength. Oh, come back. So the Greek letter lambda for this wavelength, this distance between from crest to crest or trough to trough, that distance is what we call wavelength. And I think I mentioned it the other day, it's on your equation sheet. It looks like a V with a little hat on it, wavelength. Cool. I think we're probably good with all that. Okay, so the two types of waves, now she went into some other kind of cool things about waves. But the two things I really want you to know is the transverse wave, okay, and then here in a minute the longitudinal wave, like a slinky. I brought a slinky here. Found it in the store. Okay, transverse waves. So the one with kind of the compression and expansion, like we see with the slinky, that is not that is not transverse, that's longitudinal. Okay, so we'll see this. So let's see if we can get it to work. There we go. And like she said, you can, oh, it's not going far enough. Why isn't it going far enough? Why isn't it going all the way down with it? Just something simple. I think put it on the table. Let's put it on the table. I think the friction. I don't know about you, but growing up I had slinkies that didn't last very long because they get all tangled up. So I'll see if I can. Oh yeah, that's better. So where it's squished together would be the crest, and kind of in the middle of where it's squished together would be the trough. So from crest to crest is a wavelength. Okay? Yeah. It is a big slinky. But can you see where kind of the direction of the wave is literally the direction that the energy is traveling? Whereas like the bobbing up and down of water, you basically have water going like this. And you have wave going like this. So that's at a right angle. This is in the same direction. Okay, so these are called longitudinal waves. So in this case, the medium is the slinky. Okay. The crests are the compressions, and the troughs where it's spread apart we call rarefactions. So compression, and in between rarefaction. Compression, rarefaction. longitudinal. Cool. So this would be, this is cute, must be a tiny little string, teeny. So anyway, we have this string that this guy is, or girl is moving up and down, creating kind of the ripple in the pond or the ripple on the trampoline. That's transverse, okay? And the particle displacement is at a right angle compared to the direction that the wave is moving. So again, slinky is longitudinal. The direction that the wave is moving is equal to the direction of the relocation of the particle. This kind of just summarizes again, bless you. So crest to crest is the wavelength. So I'm gonna want to be able to write that cute little Greek letter like that. Bless you. The amplitude that she talked about is kind of, it's how much it goes up, it's how much displacement, and actually that's associated with the energy. In the case of sound, the amplitude is the volume. Turn up those amps. Amplitude, right? Maybe it's amps on the electric grid, I'm not sure. So now we're getting to one of the little equations that we're gonna want to be able to apply. She talked about frequency. I like to say exactly kind of what she said. Frequency basically is if you're standing still and your wave is going by you, and you set your timer for 1 second, however many waves can pass you in 1 second, that's the frequency. So it's basically waves per 1 second. That's frequency. Frequency actually is in units of per second. So in this example, for instance, let's say you let it rip for 20 seconds, and as you're standing there, you have 20 ripples go by. So in that case, we could take how many ripples per second? We could take 20 ripples per 10 seconds. So 20 divided by 10 is 2. So that's 2 ripples. Actually, we just do 2 ripples per second. That's it. Units of frequency are per second. That's a 2, not a Z. Okay. So that's how that works. Frequency. So you've probably heard of Hertz, H-E-R-T-Z. If you do much with radios, they'll talk about the Hertz, or maybe even television, they'll talk about Hertz. And that's cycles per second. Usually it's not Hertz, but megahertz. Mega meaning 10 to the, I don't think much, it's 100,000 I want to say, megahertz. But that's, if you think of like 10,000 cycles per second, that's a lot of little ticks going past you. 1,001, you know what I'm saying? So things at high frequencies are, speaking of high frequencies, with regard to pitch, if something has a high pitch, do we say it has a high frequency or low frequency? If it's got a high pitch. High frequency. I can answer my own question. High frequency. And so literally, if you were counting the number of compressions, because actually sound is a type of longitudinal wave, if you were counting the number of compressions, there would be more compressions per second for high frequencies. And that's how our fancy little eardrums distinguish pitches. Okay, so 65 hertz means 65 wave cycles per second. Now this could be a transverse wave or a longitudinal wave. It's cycles per second. It could require medium or couldn't require medium. I've kind of picked on air as needing medium to travel through, like when you're out of space, they can't hear you scream, okay? But light is another type of wave an important type of wave we're gonna talk about probably more on Monday. And light goes like this. So it makes it transverse. So light doesn't need a medium. Pretty exciting. Anyway, so we have wavelength, it's crest to crest, frequency, the number of cycles per second. Speed is how fast that information is booking down the road. okay? And actually for speed, we're going to use the letter V for velocity. Excuse me. So here we go. I know it looks like a funky V, but that is speed. Speed is equal to wavelength times frequency. I've been kind of thinking about this class and just dabbling in physics. They do a lot of equations in physics. And I think if you take the full-fledged physics course, they will convince you why these relationships we're using, like epsilon MA, how do they know that? Okay, they'll dive into that more. I'm just kind of going to apply that. Cool. So one of the things you're going to want to be able to do is to kind of algebraically rearrange things. To me, this first version up here, I'll call this version number 1, and I'll call this version number 2. Version number 1 works well if you're after the speed or the velocity, and if you have the wavelength and the frequency. Let's just say that you have the velocity or speed and the frequency. Well, in that case, you could knock out the wavelength. Now remember, to go from version 1 to version 2, let's see what we're doing. We're dividing by frequency. Does that seem right? Yeah. So that's just a rearrangement. We have one more rearrangement. This is version 3. And again, depending upon what you want to solve for. If in this case we were after frequency, we'd do it this way, because we must have been given velocity and wavelength. Especially in my other classes, and a little bit in this class, you guys are using your units. Units are your friend. That's all a good thing. I'm going to kind of show you how this works. So, for instance, velocity or speed. What units do we use for speed if you're driving down the road? Miles per hour. Yep. Speed, I'll go ahead and just I'll put V for velocity. And you give a direction, miles per hour. So bottom line, miles is a distance, right? And hours is a time. So I know this is really messy, but I want to focus on version number 1 right quick. Velocity or speed of a wave. I'll go ahead and answer my own question. Well, I'll do it this way. Wavelength is in units of length, which is the distance in this case. So velocity, for instance, our wavelength might be in units of meters. And what are the units of frequency? Do you remember? I'm counting 1 second, how many cycles? So it's per second. Yeah. It's just per second. So we have meters, and I'm going to multiply that per second. It's going to be like this, per second. So here I have velocity is meters per second. The velocity of a wave. And my point with asking you about when we say what's the velocity of a car, of course with velocity we need to make sure we get direction too, but with regard to its speed, its distance, its length, time. All right, so let's do a problem. Let's do a couple problems. Do you guys have this problem? Okay. And at the top, and Ashley was asking about the equation sheet I gave you, but I will give you an equation sheet for sure that will say V is equal to, what did I say, wavelength times frequency. Okay, consider a sound traveling with a speed of 344 meters per second. So of those 3 variables, which one is that? What is the 344? Is it the V, The wavelength is the velocity, the wavelength, and the frequency. I'm thinking velocity. And this is where this sort of problem, I don't know about a picture necessarily, but I'm going to just go ahead and I'm going to call that speed, the velocity, I'm going to go ahead and say V is equal to 344 meters per second. It's like picking apart, it's like dissecting. V is equal to, oops, goodness, 344 meters per second. My pen's kind of going wacko again. Okay, what's the next word? What's that 0.55 m? What is that? Wavelength? Yep. So I'm going to put a little semicolon, and I'm going to put wavelength is equal to 0.55 meters. And then while I'm jotting things down, I'm going to put frequency is equal to question mark. So of those three that we looked at, I think was it the previous slide, first version, second version, or third version, which version are we going to use? Right, the frequency is equal to the velocity divided by the wavelength. Does that make sense? And so when you knock this out on the test or homework, don't forget to include your units. So here we go. Frequency is equal to the velocity. Can't read my own writing. That got me into trouble the other day. 344 meters per second divided by the wavelength, which is 0.55 meters. Now, again, on your homework, unfortunately, sometimes it'll make you like convert units, like from kilometers to meters, but on a test, I won't do that. Now, do you see where actually the units of meters in this case cancel out? Meters will cancel out. So actually, I just have units of actually seconds in the denominator, because this is per second. So unit-wise, when meters go away, I get so excited about units. So I have units of per second. So that's awesome. So how are we going to round this one? 1, 2, or 3? I'm thinking 2. We're going to go 2 because it's always fewest. So we're going to go fewest. That has 2. This 0 doesn't count, and this has 3. So let's see. 3.4. I got 625.45 repeating, it looks like. So my calculator displays is 625.45, and that's units are per second. So if I'm going with 2 digits, I'm going to keep this digit in the hundreds place, keep the digit in the tens place, and I'm going to lop it off. So do I round the 2 up or leave it 2? I'm going to round it up, but I'm going to have to make sure I put that kind of 0 after it to make sure I show magnitude. So 630, and then units are per second. Make sense? What other units are, did I say just a minute ago, are per second? Starts with letter H. Hertz. Yep. Hertz. I always think of, and it's a dumb joke, so I know, so you go up to your sister or something, you're like, hey, you want a donut? And like, sure. And so you hit him in the arm and you say, Hertz, donut. I know, it never gets old, but anyway, yep, that's a hertz. So we could say 630 hertz, which is Hz. Cool. Okay, let's do the next one. Sound generally travels faster in the denser medium, thus it travels faster in water. What is the frequency of a wave with the same wavelength, with 0.5 meters, traveling now at a faster speed? Okay, so it looks like we're going to use the same equation. What is the frequency? So in this case, my wavelength is the same, 0.55 meters,
And my velocity now, wow, is instead of 344, it's 1,500 meters per second. So what do you think? Is that the frequency going to be higher or lower? How many people think it's going to be higher? How many people think it's going to be lower? Well, I think it's going to have to be higher because the velocity is in the numerator and that number got bigger. So just eyeballing it. So let's do it. Let's do this thing. So frequency is equal to, we said velocity over wavelength. So now we have 1,500 meters per second in the top, and in the bottom we still have that 0.55 meters. Our meters cancel. We have units of per second, which is the same as hertz, don't it? We take 1,500 divided by 0.55. I actually heard from my brother indirectly today, and he accused my Honda Fit as being driven by rodents. You know, like rodents are in the... He's like, I saw a dead rodent. I thought that was yours. It fell out of your car. I'm like, are you serious? Oh, I never get back at him. I just never can. So I got 27 repeating, but I got 2727.27. Okay, so how many digits are we going to round it to? I'm going with 2. So we're going to keep this first digit, this next digit, we're going to lop it off. So what is our answer going to be? So 2700. 2,700. And units are either hertz or per second. What do you think? Works. Works, don't it? Oh my goodness. Okay. So that's actually how far I wanted to get. So that's all good. So this will be due when we meet on Monday. Chapter 6, page 164, number 4. And I just said to remind you when the number 4 must use words like distance between crests, and that we know is the wavelength. So is that one? Oh, we already have it on there. Yay! Let's start with it. So that's not bad. Did it again on Monday. Does anybody have their textbook here? Just double checking. Okay, thank you. Maybe it's just exercise sections. So it doesn't work section. That doesn't even make sense. Is anybody else having trouble that the answers aren't working, matching up with the questions, kind of? They're weird, like they don't fit. But the answers I have posted.
This one, this one, when I went to double check, there's 6.
This is applying knowledge.
Yeah.
But this is
Applying your knowledge. 1.5. So we have to do, I thought they don't have to do number 4. So what number 4? Or on the exercises. Okay.
But I see what you're saying, your report is still
Like
taken.
number 4 is a piece of power because of more energy. So we're unit time. So I looked at, I went back to the chapter. I didn't do that.
So maybe that's the answer to this, but it doesn't totally answer your question. Yeah, but I see the confusion. That it could be that hopefully that's just an isolated
I didn't know if maybe this was one that I had two. I see one and two, but now.
I rarely, there's different sections, different types of light.
I'll do exercise.
Okay,